Right, good afternoon. I'm Wally Macfarlane, and over the next 15 minutes, I'll provide an overview of our Riverscape's network assessment of Lahontan cutthroat trout habitat. This is a 2-year project, which is initiated by the U.S. Fish and Wildlife Service. So there's a core recovery team that contracted out with us to do an assessment of habitat. I would like to acknowledge my co-authors, Nick Bowis of Utah State University, and also Ecological Research, and Philip Bailey of North Arrow Research. So just an outline of what I'll cover in this presentation. So first, I'd like to help provide a conceptual background for a habitat assessment approach, and I'll provide an overview of a fairly new stream evolution model that describes different stages of a stream that a stream might go through over time, ranging from incised and disconnected from its floodplain to a stage with multiple threaded channels and high lateral connectivity, which is referred to as stage 0. Next, I'll make a case for why lateral connectivity is an important indicator of fish habitat quality. Next, I'll describe how lateral connectivity will be assessed in this project using the riparian condition assessment tool. And I'll finish off the presentation by providing the primary applications of this habitat assessment. So I don't know how many of you have seen these stream evolution models. This is one by Kluwer and Thorne in 2014. And you'll notice as you go through around this, these describe different stages from intact to degraded, and then going back to widening and improving, and back to a multi-threaded stage, which we refer to as anastomosing or stage 0, where there's high connectivity with the valley bottom and high resilience and habitat diversity. In this incised state, channels and floodplains are disconnected, and these stages have limited fish habitat quality, complexity. Here's an example of incised and highly degraded stream. I'm sure many of you in your travels throughout the Intermountain West, the Southwest, have seen streams like this. They're heavily incised, they're down cut. The floodplain is now converted to upland species. There's very limited riparian vegetation. Here's an example looking more from an aerial view of this incised, disconnected floodplain stage. The idea here is this has been degraded by down cutting, by incision. And so the historic valley bottom was all active floodplain. Now the current condition is you have this incised channel with a very narrow active floodplain with a wide inactive floodplain. So this anastomosing state at the top, there are examples throughout the Intermountain West of this, and in this case, this is the Marys River in Nevada, part of the Lahontan cutthroat habitat assessment area. And just looking at this here, we have a valley bottom out to here. This whole area is active floodplain. We have multiple threaded channels. We have high lateral connectivity, and we have complex trout habitat. So this is what we're shooting for. This is our target. So next, how are we going to go about how and why are we using lateral connectivity as a proxy for fish? Kind of to build our case, I have 2 examples. The first is Bridge Creek. This project involved studying how can beaver dams and beaver dam analogs accelerate the process of incision recovery? And can this benefit fish populations? So that idea that currently is a very incised stream, and through these restoration activities where 240 beaver dams were built along with BDAs, and then the fish response, the steelhead response is pretty remarkable. 168% increase in abundance, 52% increase in survival, and 172% increase in productivity. Another example, that's cutthroat fish. This is in Birch Creek, Idaho. In this project, we reintroduced 9 beaver, and over the course of 3 years, they built 140 dams and just transformed the riverscape. So this is the first time in 40 years there's been perennial flow throughout the system. Prior to that, it would dry up in the fall or late summer, fall. So trout have increased 50-fold from previous surveys, and beaver complexes have increased 10-fold. So pretty remarkable transformation of this riverscape, and at the same time, the effects on trout populations. So how do we plan to go about assessing lateral connectivity and using it as a proxy for habitat quality, fish habitat quality? So pretty simple. The idea is that the current extent of riparian vegetation with the valley bottom will be used as a proxy for lateral connectivity. So in this example, this is high lateral connectivity, so this would be scored very high. So the higher the proportion riparian vegetation, the higher the lateral connectivity. And we'll use the riparian condition assessment toolbox to do this assessment. The riparian condition toolbox, maybe some of you have heard of it, RCAT. It's comprised of first a valley bottom extraction tool. The idea here is the valley bottom is this area from this hill slope to this hill slope. It includes the floodplain and the channels. Riparian vegetation departure, RVD, is the second tool, which we'll talk about, and then the riparian vegetation conversion type, as well as the riparian condition assessment. These are currently being run with readily available nationwide data, and we're fortunate enough next year to be able to run these same models with NDVI derived products from Ken McGuire at Desert Research Institute. And he's developed a riparian vegetation map for the state of Nevada, which is a very useful product. So let's go into a little bit of more detail on each of these tools. So on the valley bottom extraction tool, the idea here is that there's thresholds that we can use within a drainage area, which will have different slopes. So for example, in these lower valley bottoms, you might have quite a bit flatter slopes than compared to, say, these tributaries here, these main tributaries, compared to these headwaters. So the idea here is that we can derive valley bottoms throughout the whole drainage area if we use these thresholds and these different slope estimates. So the valley bottom becomes input into the riparian vegetation conversion, riparian vegetation departure. So this is simply O to E, so observed versus expected. So in this case, we have a valley bottom. We have it broken up into these polygons, these segments. And so here's our existing vegetation divided by historic, so our O to E, and we come up with a riparian vegetation departure. And these values are showing how much they've changed from historic. So in this case, large departures are 66% or greater, and this has been run throughout the state of Utah. So the riparian vegetation conversion type, RVCT, just looks at the historic riparian and provides a output of what it's transformed to. In this case, there's conversion to agriculture throughout this example area. In the places you folks work, likely there'll be a lot of conversion to invasive. So it gives you that idea of what changes we're seeing from historic to current. And then the riparian condition assessment, RCA, brings in RVD, so riparian vegetation departure, and land use intensity. This might be agriculture versus pasture versus just open area. And then importantly, we also look at floodplain connectivity. And here we look at how roads, railroads, and in some cases levees and dikes have broken up, fragmented the valley bottom. So in this case, red represents disconnected floodplains and blue are still intact. And these are all combined within a fuzzy inference system to provide a output that's reach-based, but can be run throughout a whole riverscape. So in this case, what we see throughout this study area is we have some, still intact areas in good condition versus those that are in poor condition. In this case, probably driven by agriculture. And then in the headwaters, because headwaters really don't have a valley bottom, we just stick with confined, impacted, or unimpacted. So I'm just going to provide some quick examples of the riparian condition assessment tool in Utah. And this case study is another Birch Creek. This is in southern Utah. And this is, first we can see the valley bottoms are in green. We have a zoom in area, which is a restoration area. This is a Bonneville Cutthroat trout habitat restoration project and sage grouse habitat. So you can see out here, there's been a lot of pinyon juniper removal. Within the valley bottom, there's been a lot of vegetation encroachment and incision. So if we look at the tool outputs, the riparian vegetation departure shows large departures in the upper reach, and then some changes from minor departure to major to minor to major. And this corresponds with the vegetation conversion type. We see here that we have conifer encroachment significant up here, and then less here, and then in the lower, there's just really not much change since historic. And then if we look at the riparian condition assessment, we see poor condition up here. This is this corresponds with the highly incised area where it's disconnected from its floodplain. And then we have moderate to good down in this area. I got to turn off my phone really fast. So that's the riparian condition assessment. The primary applications of this Riverscape assessment and the projects you guys will work on will probably have similar applications, but we see it as helping to identify both conservation and restoration areas, and those areas that should be prioritized because they're likely going to have the greatest benefit for, in this case, the Lahontan cutthroat trout. And this helps prioritize where restoration work is done and then ongoing monitoring. I think this is a case for the importance of assessments. A lot of us talk about restoration and monitoring. But a first step is to assess what the condition is currently. So it's very important. And this helps with the establishment of recovery potential. As we look at what the current state is, we can also gauge where we can get gains, where we can have the greatest recovery potential. And then finally, this is very important information in developing conservation and restoration plans. So in this case, Lahontan cutthroat trout, this could be applied to other species. And the idea is these can be really important inputs for those plans and the assessments that follow. With that, I'd just like to acknowledge my co-authors and the development team and those that have helped throughout the development of RCAT. Many people to thank. And with that, I'll leave it open for questions. Thank you.